Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Today, we will going to discuss about differential pulse code modulation. These are the outlines. We'll start up with the introduction where we will try to give the need for differential pulse code modulation. Then we will discuss principle of differential pulse code modulation. Then we will try to give the reasons that why do we need a predictor. Then we will discuss differential pulse code modulation transmitter followed by DPCM receiver, and then we'll going to discuss various advantages of differential pulse code modulation over the pulse code modulation systems, and finally we're going to conclude via describing some of the applications of differential pulse code modulation. In our last lecture, when we discussed about pulse code modulation, we have discussed that for encoding each sample value, we are providing equal number of bits independently of all other samples. If we closely observe about the audio or video signals, then we could say that there exists a very high correlation between the adjacent sampled values. I mean, they are highly correlated, or there exists a very high degree of similarity between them. So if the audio or video signal is sampled at the rate which is slightly higher than the Nyquist rate, the resulting sampled signal is found to exhibit a very high correlation or similarity between the neighboring samples. It means that the average change in the amplitude between the successive samples or adjacent samples is relatively small, or we could say that they are almost similar. In other words, we could say that the PCM is having much redundant information. By redundant information, we mean the duplicacy. So by removing this redundancy before encoding, we may obtain a much efficient coded signal, or we could say that we are in a state to pass our signal with lesser number of bits. So hence an encoding scheme that exploits the redundancy in the samples and results in a lower bit rate for the source output is required. Obviously, we wanted that with the help of fewer number of bits, we can pass maximum amount of information. This is what we wanted in any communication system. So whatever we have studied so far, let us try to understand it with this figure. Let us consider this sinusoidal signal. Here this orange color wave shape, this actually shows our input signal. Then the sampled version or sample value of this signal is given by this blue color dots. This basically represents the encoder output. These are nothing but these are the certain codes which has been assigned to these such quantized levels, and depending upon in whichever quantization zone our signal will going to lie, depending upon that we'll going to generate that 4-bit coded sequences as per this example. So if we closely observe this particular sample values, then the adjacent or neighboring signals or sample values are highly correlated, or they are almost same. So now we are going to discuss the principle of differential pulse code modulation. So in DPCM, what we actually do is we will going to encode the differences between the successive sample values rather than the individual samples, as we did in our PCM systems. So since the differences between the samples are expected to be smaller than the actual sample amplitudes, since signals are highly correlated, or there exists a very lower differences, so fewer bits are required to represent those differences. Obviously, if we are comparing about encoding individual sample values and encoding the difference values between two contagious sample signals. So in this case, we can quantize and transmit the differenced signal sequence. So here En represents the difference value in the signals. Xn and Xn minus 1 are neighboring sampled values of our signal Xt. So now after understanding the principle of DPCM, let us understand the need of predictor, what it is and why do we actually need predictor. So it has been observed over our audio and video signals when the sampling rate is set at the Nyquist rate, that is equal to twice of Fm, it basically generates a very high amount of quantization noise. So if we increase the sampling rate, the quantization noise may decrease, but the bit rate of DPCM, that is number of bits per sample into the sampling rate, may exceeds the bit rate of the PCM. So if this is the case, there will be no utility to use the DPCM, since the bit rate of PCM and DPCM both are equivalent to each other. So this case can be improved by recognizing that there is a correlation between successive samples of the signals. So a natural refinement of this general approach is to predict the current sample value on the previous samples utilizing the linear prediction methods, and the linear prediction parameters should be estimated dynamically. That means on the runtime we will going to decide how we will going to utilize the linear prediction mechanism to predict the current sample value. So hence, what is predictor? If we talk about predictor, predictor is something which will going to predict the current sample outcome based on the previous samples, and they are predicting the current sample value via exploiting some linear prediction mechanism which are dynamically estimated. Now we're going to discuss the block diagram structure of DPCM transmitter. Let us assume that the time varying message signal Xt is sampled at the rate of 1 by Ts to produce the sequence of highly correlated samples at Ts seconds apart, which is denoted by x of nts. I mean, if signal xt is sampled at the rate of fs number of samples per second, then the relationship between the sampling period and sampling frequency will be fs is equal to 1 by ts. I mean, after ts second, we will going to get the next sample. Due to the predictor, it is possible to predict the future values of the signal xt on the basis of past values of the signal. So basically, we are trying to predict the current sample value on the basis of past values of the signal. So this is what our predictor will gonna do. So in DPCM transmitter, initially we will going to have input sample value. The time varying signal xt will get sampled and we'll get some sampled output as x of nts. Then after that, there is a summer. The function of this summer will get explained after some moments. Then that particular signal will get passed through the quantizer, which will going to quantize the incoming signal, and that incoming signal will get passed through the encoder, which will going to generate the coded signals on the basis of quantizer output, and the output of the encoder will be our DPCM output. Basically, this transmitter figure is little bit complete. Now we will try to describe the role of this summer and the remaining part of DPCM transmitter. So now this particular whole figure will shows the DPCM transmitter. So what we're going to have is the second input to this summer is our prediction filter outcome. So as we had already discussed, that prediction filter or predictor is something which will going to predict the current value depending upon the past values. E of nts is nothing but the prediction error, which is the difference between the incoming sample value and the present predictor outcome. This would have been denoted by E of nts. Then that error signal E of nts will get passed through the quantizer. Here EQ represents the quantized version of the error signal, and that error signal will get passed through the encoder, and the output of the encoder will be our DPCM output. In the meantime, as we had already told that the prediction mechanism, the linear prediction mechanism is dynamic. I mean, various parameters have been dynamically estimated. So the input to this predictor filter is the quantized error signal and the previous version of our predictor output. So combined fashion, there is another summer which will going to the summation of quantized error signal and previous predictor output, that will be the input of our prediction filter or predictor. So on the basis of previous predictor output and the error signal, predictor filter will going to generate the current or present prediction output or sample value. So the major job of prediction filter or predictor is to generate a sample value which is almost equivalent to incoming current input sequence. So this is all about the differential pulse code modulation transmitter. Now we're going to discuss it into the greater detail with some mathematical equations. So the input to the quantizer is being given as error signal will be given as sampled version, current sampled version subtracted with the current predictor output signal, which is the difference between the unquantized input sample, that is x of NTS, and the prediction of which it is given as x cap of NTS. Here this x cap sign basically represents the output of the predictor. So this predictor value x cap of NTS is produced by using the prediction filter with an input that consists of the quantized version of the message sample x of NTS. So now again, what is the difference signal? The difference signal E of NTS is called the prediction error. If predictor would have been able to predict the current sample value accurately, then the difference signal, or we could say the error signal, the value of error signal will be 0. But since predictor is only predicting the value with some probability of being correct, so the amount by which the prediction filter fails to predict the input is termed as the difference signal or the error signal. So by encoding the quantizer output, we obtain the variation of PCM, that is known as the differential pulse code modulation. So here the difference has been quite clear between the PCM and the DPCM, that in PCM we are basically encoding each sample value, whereas in DPCM we are trying to encode the error signal. So it is encoded signal that is used for the transmission. So now if we closely observe this DPCM transmitter block structure, the output of the quantizer is being given as EQ of NTS, which is nothing but it is the summation of E of NTS plus Q of NTS, where Q of NTS is nothing but it is the quantization error while performing quantization over E of NTS. So as per the block diagram, the quantizer output EQ of NTS, this EQ of NTS is added to the predicted value of x cap of NTS, this one x cap of NTS, to produce the prediction filter input. Hence the input to the predictor is being given as xq of NTS is equal to predictor output plus the quantized value of error signal, where EQ of NTS is the quantized error signal. So now from this above discussion, we may write that xq of NTS or the quantized version of x of NTS will be equal to predictor output plus error signal plus quantization error. Since predictor output and error signal combinedly gives us this x of NTS, and this is the quantization error. So here xq of NTS is the quantized input to the prediction filter, and the summation gives us the input sample value. So irrespective of the properties of the prediction filter, the quantized sample value, that is your xq of NTS at the prediction filter inputs, differs from the original sample x of NTS with the quantization error q of NTS. This is what we had already seen through the block diagram of DPCM transmitter. If the prediction filter is good, the variance of the prediction error will be smaller than the variance of x of NTS. What point I want to make with this statement is, if predictor is in a state to predict the incoming sample value exactly, then the error or the difference between the predicted value and the incoming sample value will be very much less, and we will require very fewer number of bits to encode that difference or error signal. So variance basically the square of standard deviation. We are not going through in much greater detail about the variance, but essence should be clear that if we do not perform this DPCM operation, then what we're going to do in our PCM is we have to individually encode each and every sample value independently. But if the prediction filter is good, then the variation in the prediction error will be much smaller in the variation in the x of NTS, or we could say that the contiguous or neighboring sample values, that is x of NTS and x of n-1 TS. This means that if we make a very good prediction filter, it is possible to produce a quantization error with a smaller variance than if the input sample x of NTS is quantized directly as the standard PCM, which basically serves the purpose of using DPCM. But here the predictor will going to play a major role. If the predictor output is almost equivalent to the upcoming sample value, then only this holds good. So now in this particular slide, we're going to discuss the DPCM receiver. So DPCM receiver basically consists of a decoder and the same predictor filter that we have been used at the transmitting side. So initially we'll be having an input signal, which is nothing but the bits, or we could say that the bit stream of error signal. Then our decoder will going to decode those bit sequences and generate some quantized version signal, and it will get added up to a summer. The another input to this summer is the prediction filter output that we have been used at the transmitting side. The output of this summer is nothing but the prediction filter input, which will get combined with the error signal, and at the output of this summer will be our exact input signal. So this is our differential pulse code modulator receiver, or we could say that decoder. So now let us discuss the working of DPCM receiver in much greater detail. So the receiver, for reconstructing the quantized version of the input signal, that it has been shown in the block diagram. So it basically consists of decoder to reconstruct the quantized error sequence. This is what we had already discussed. Then the quantized version of the original input is reconstructed from the decoder output using the same prediction filter as used in the transmitter. So combining those predictor filter output and the quantized version of the error signal, we will get the quantized version of the original input signal. So if there is no transmission noise, the encoded signal at the receiver input is identical to the encoded signal at the transmitter output. But please note that if there exists some noise, then we will going to have some distorted received signal due to the presence of noise. So in the absence of noise, the receiver output will be equal to the quantized version of input signal differs by sample value by Q of NTS, which is the quantization error caused by quantizing the prediction error E of NTS. If we closely observe the DPCM transmitter, then this relationship is quite obvious. So now various advantages of DPCM over the pulse code modulation. So obviously the bandwidth requirement of DPCM is very much less in comparison to PCM. The reason is quite obvious. In PCM, we are encoding individual sample value independently, whereas in DPCM, we are basically transmitting the difference between the predictor output and the incoming sample value after quantizing and encoding. So if the predictor is producing some accurate result, then the resultant error signal will be very less, and there are very fewer number of bits that are required to encode the difference signal. So quantization error is reduced due to the use of prediction filter. This is what we had already discussed, and it is quite obvious too. Obviously, if the predictor output is equivalent to or equal to the incoming sequence or sample value, the quantization error is reduced. Number of bits used to represent one sample value are also reduced in comparison to PCM. So if we have to map larger amount of amplitude levels, then obviously the number of bits requirement will be higher, and if we have to encode the lower levels of amplitude values, then the bit requirement will be much lower. So basically first advantage and third advantage both are analogous to each other. I mean, if we are using lesser number of bits to pass larger amount of information, obviously we could say that the bandwidth requirement of DPCM is very much less. And since bandwidth is a very scarce resource, so this is our wanted phenomena too, or this is what we wanted too. So now the applications of DPCM. DPCM techniques are mainly used in speech, image, and audio signal compression. Since we wanted that with fewer number of bits, we could pass more and more amount of data. So this method is suitable for real-time applications of medical imaging, such as telemedicine or online diagnosis. It can be efficient for lossless compression and implementation for lossless or near lossless medical image compression. So I mean, if we are doing some medical tests and if we are getting certain images, then obviously we want to transmit those images without having significant amount of loss. We always wanted to pass them from one point to another point. So for that sake, DPCM has been used. These are the references that we have used for preparing these slides. Thank you very much for your patient hearing.